welcome to the third day for the 2022 playoffs for the AI and 5G challenge. For those who were not here yesterday or the first day, this is just a friendly reminder that the presentation should be 10 minutes long, and which will then be followed by a 5-minute Q&A session. Without further ado, I'd like to introduce the first problem statement, build your own closed loop. I'd like to welcome on stage Team Digital Twins to start on their first presentation.
Yeah, thank you. Can you hear me?
Yes, I can.
Okay, may I share my screen?
Yes.
Can you see the screen?
Yes, we can.
Okay, thank you. So I will start. Okay, hello everyone, and welcome to this presentation, which title is Evolution of Blockchain and Autonomous Network Architecture Proof of Concept. This contribution has been developed by my colleague, Jaime Fuster de la Fuente, and myself, Álvaro Pendas Recondo, in the framework of our internship at Rakuten Mobile. And we have been mentored by Paul Harvey. What we have done is to implement a decentralized architecture for the evolution of controllers in an autonomous network. And for that, we build a marketplace using some technologies that I'm going to explain during this presentation in order to meet the requirements of trust, integrity, auditability and traceability, fault tolerance, and scalability. But in order to explain this, let's start with some questions. First, where do we come from? Then, what is the problem that we wanted to solve? What is our solution? And finally, does it work and why it works? And after that, we will have some time for questions. Okay, first of all, where do we come from? We initially presented this contribution to the ITU Focus Group on Autonomous Network, Bilathon 2022, which title was Build Your Own Closed Loop. But now is appropriate to define the concept of an autonomous network. You could say that autonomous network is an artificial engineering. That means that it's a network where there are some nodes that, of course, are going to use machine learning models to solve problems that they have been trained for. But the concept of autonomous network goes beyond that, and is a network that has the ability to heal itself. That means that when a new problem appears and the network has not been trained in advance for that problem, it still has the ability to find a solution. In order to do that, there are two tools that are used, modules and controllers. Modules are pieces of software that are designed by engineers and uploaded to the network. And the network is going to combine those modules into controllers in order to find the best tool for each problem. How are controllers composed? Or how will we get to each specific controller? Via evolution or evolutionary algorithms, mimicking the same thing that living things do. Why do we use evolutionary algorithms? That's because they are really good in coming up with solutions that people did not think about beforehand, and therefore really effective when it comes for the network to find the solution from a problem that it has never trained for, that specific problem, and therefore it's a new problem. It has not seen that problem before. However, like, this idea is really good on paper, but the question that we made ourselves is, how do we make evolution happen? For that, we first took a look at the architecture proposed in the Focus Group Autonomous Network Input Document 198. The question was, how can we implement this and make it a reality, right? And right since the beginning that we start working, we identify some problems, some issues, that here there is a list of the most important of them. First, how do we keep track of the changes that happens in the evolution? Then a security problem, how can we trust its node information exchange? Then where is the information stored? And after that, how is a controller deployed after being stored? Like, after the evolution happens, how can we automatize the deployment of a controller? So that is like an introduction to the problem. Now I will present our solution. Here is our proof of concept architecture. And the blue nodes are denoted as actors and the green nodes are denoted as elements. We first start with an evolution controller, and the evolution controller on the right is where modules are stored. And that is going to combine some modules to produce an evaluable controller that has to be tested. So in number one, that evaluable controller is uploaded to a marketplace, and the marketplace forwards that, number two, to an experimentation manager. The experimentation manager configures a digital twin that is going to run some experiments and responds with some key performance indicators. With that information, the experimentation manager produces an experimentation report that uploads to the marketplace in the number 5. And finally, we have a curation controller that is going to decide which controller are promoted to the category of protected controller. That means a protected controller means that it's going to be used further in the evolution process because it performed well enough in the experiments. So again, this is like a good idea, but we still have the problem with the marketplace. With all the important information is stored, we still have the problem of security and unique point of fault, right? So how do we solve that problem? The question here is how to store and access artifacts in a traceable and secure manner. The requirements that we wanted that I introduced before are trust, integrity, auditability and traceability, fault tolerance, and scalability. And in order to meet these requirements, we use the technologies blockchain, being more specific, Ethereum for decentralization of the system, and IPFS, which stands for Interplanetary File System, for distributed storage. With Ethereum, we created a private permission blockchain where smart contracts are written every time an artifact is uploaded. And with IPFS, allowed us to implement a distributed decentralized file system where integrity of the documents are ensured via a content identifier. Therefore, every time the nodes exchange information, they do that in JSON, and we chose JSON format because it's readable by humans. A smart contract is written in Solidity, and therefore that exchange is being stored, and also the information is uploaded via IPFS, and all the nodes have access to that information. It's important to remark that actually the marketplace is distributed everywhere, although in this scheme we represent it as only one node. Is in our distributed solution is present in all the nodes of the network, and that's why it's a decentralized architecture. In order to test this architecture, we had to implement some modules, and for that we coded some Python classes using just simple mathematical equations. For example, here we have a module that just multiply by 3, given a first-time input. Controllers are also Python classes, but they are composed by a list of modules and a list of parameters tuning those modules. In this case, we have the module minus and the module multiply, tuned with the parameter -2 and multiply by 10. So in the evolution, the network is going to try to find the best controller for the user, depending on the user requirements. It might be, in this example, the mathematical equation for finding the highest value, or for yielding a specific output given a specific input. Explaining in more detail some implementation details that we explained this in the report. On the Python side, we use the framework Flask for the HTTP server and Unicode for concurrency. As I said, JSON is the format that we chose in order to exchange information because it's readable by humans. And the JSON files are exchanged via HTTP. On the marketplace side, we use JavaScript. And also, in order to get the whole network running and testing everything, we use Docker containers. Here you can see some JSON representations that are stored in the marketplace. The representation of a controller with the models that it's composed of and the parameters tuning those modules, the result of an experiment report, and the certified for a protected controller. And this is in the marketplace that again is distributed in all the nodes of the network, and every node in the network have access to this information. We still have one more problem to solve, and that is the automatic controller deployment. For that, we wrote some code in Tosca, which stands for Topology and Orchestrator Specification for Cloud Applications. And that can be executed by orchestrator. We chose Xopera. So given a controller CID, the CID is the address of the controller in the marketplace. The code that we wrote is going to automatically pull that information from the marketplace and deploy a REST service that is hosted in a Docker container. that when a client connects via HTTP GET petitions, it's going to respond with an HTTP response with the output produced by the controller. And therefore, we automatize the process of a controller deployment. So finally, the question is, does it work? Well, recalling the initial issues, we have solved the problem of track of changes and trust thanks to Ethereum and smart contracts in Solidity. About the storing information, we do that in a distributed manner thanks to IPFS. And we automatize the process of controller deployment thanks to writing some code in Tosca, and that is executed by the orchestrator Xopera. So thanks to the architecture that we thought and also the marketplace that we built, we met the requirements of trust, integrity, auditability and traceability, fault tolerance, and scalability. And we met the ultimate goal of making evolution possible in an autonomous network in a distributed and decentralized manner. So that's everything on my side. Please go ahead and check our GitHub where we have all the code. Also in the report, we explain further about all the implementation details and future work. And in the GitHub, we also have a video demo that you can watch. And of course, you can clone the GitHub and try test this in your local machine yourself. So now it's time for any questions that you may have.
Thank you for your lovely presentation. Do any of the judges have any questions? Okay, then I'd like to open up the floor to audience members and other competing team members. Does anyone have any questions, comments?
Maybe I can quick comments. Alvaro, first of all, thanks. A lot of great work has gone in, a lot of hard work, and thanks to Paul for mentoring you guys. The three metadata formats you have used. It's quite interesting. Quite interesting your demo. First, you have used JSON. Second, I guess Docker comes with its own metadata. Third, I guess you're using Tosca. Could you please explain your experience working with these three, if you have experience with these three in this project, and where they play a role? I think JSON is quite clear. I think you explained that JSON metadata quite well. I don't know whether you have some intersection with Docker metadata, and I don't know whether, I mean, it was not very clear from your presentation what you do with Tosca. Could you please explain what you understand from these three metadata? Thank you.
Yes, thank you, Vishnu, for your question. So yeah, starting with JSON, which is the most simple one, I think. JSON is great to work with. I like it. Again, like we chose JSON not only because it's simple to work with, but because it's readable by humans, right? So when information is exchanged among nodes, you can go there and see what's going on, right? This is an evolution that is going on in the network in an autonomous way, but it still is good for a human to take a look and see what is going on. About Docker, yes, Jaime and I, we have some experience with Docker, but that's more like because we use it in classes at university. But I think Docker, what is great about Docker is that for us, it was really good for testing. But again, like if you want to deploy this in an actual service, you still use Docker, or you can still use Docker. So that's great about Docker, I think. Like, it's really clear to write the whole like deployment. The great thing is like if you, for example, now clone our GitHub repository, it's going to work as well in your local machine thanks to the Docker containers and the architectures, and that's why we chose Docker. And again, great for testing, but also great for final deployment. And the other one, Tosca. So about Tosca, we didn't have previous experience, and it was by far the most difficult to deal with because there are not many examples. So we had to read a lot of documentation. However, I cannot say that it's difficult because at the end it's like XML format, right? You just the problem is like you have to read the documentation, and if you read the documentation, everything is clear. And what is great is you are going to get exactly what you wanted. And again, with Tosca, it's going to work in my local machine, but if you reproduce the code, it's going to work in your local machine as well, as long as you have like the package needed. So it's like Docker, very good for testing, but also really good for final deployment. But it was the most difficult one because there are not as many examples as in Docker.
Cool. Thanks. Yeah. I would like to add, maybe JSON is the same format used by this Neo4j graph format. So you know it may be naturally easier to use. That's just my observation. Yeah. Thanks.
Just a quick question from my. Okay, Evelyn, please go ahead.
Thomas, you can ask, then I can.
No, mine is more or less like a comment / a
Okay.
question. So you are the judge, so you can go ahead first.
Okay, thank you, Thomas. Thank you, Alvaro. It was a nice framework and system. I have just one question. By looking at your report, I can see that you consider the digital twin scenario, right? Can you say that such a framework be adaptable to different kind of scenarios also, like, I mean, a scenario that requires very low latency or very high EMBB, URLLC, or MMTC, I'm trying to say. Can you adapt this framework to different scenarios requiring different performance? I mean, in what point you can do some modifications?
Yes, yeah, that's like a really good question. We use the concept of a digital twin, but as you may know, we don't implement an actual digital twin, right? That would be like a lot of work. But we use the concept of a digital twin because it's the concept that is used the most in the focus group autonomous network. But the key here is like our idea was to lay the initial work in terms of architecture, build a skeleton for this, right? But then there is like plenty of future work to be added. And our idea was like, no matter the requirements of the future work, this can be used still. So of course, yeah, the only thing that you need, imagine that you have another service that is not a digital twin, that can run experiments or produce key performance indicators, and is like time efficient and has some constraints. In order to put that to add that in our architecture, what you need to do is some kind of front end that allows that node to communicate with the other nodes of the network. You just need some code for sharing JSON files, and also add that, but that is already part of our contribution, add the marketplace side, right? But just like you have whichever application, you just add some front end for exchanging JSON files, and you are like all good to have access to the rest of the network. Not only to send your results and your information, but also to access the information that other nodes produce. I don't know if that answers your question.
Okay, Alvaro. One more question. Maybe this is out of scope, but have you got a chance to try this experiment on a practical scenario in considering the digital twin scenario? I mean, you tell that in the report this is proof of concept. So maybe I don't know. This is out of scope of this challenge, but I just wondering about this. Have you got a chance to try it in a practical way?
So for the digital twin specifically, no, because there is like that's work in progress. There is still a lot of people working on developing a digital twin for solving problems in a network. What we did was, as I said, like a simple proof of concept for not simple in terms of architecture, but in terms of testing. What we did is, okay, the user has some requirements for a mathematical operation that says, okay, given this input, I want this output, and this our architecture, our proof of concept, via like combination of modules, is going to find the mathematical equation that in our case is a controller that gives that result. That's the scenario that we implemented. But if a more complex scenario is thought, that can be like run without changing the architecture. That's also the key point.
Okay, Alvaro, thank you.
Yeah, maybe I can quickly add, everyone, that yeah, of course, this team was not tasked to do that. You're right. So what we plan to do is maybe as a later work to try out more complicated closed loop scenarios as exactly the same framework that Alvaro is saying, but maybe more complicated controllers or closed loop. That's future work.
Yeah, that's actually in our report. That's described in the future work. Like to try more.
Okay, thank you, Vishnu, Alvaro.
Thank you very much. So time is up now. Thank you very much for your presentation.
Yeah, thank you for the opportunity, and thank you to the judges for their time.
I'd like to next call for Team AI ML SSD.
Hello, am I audible?
Yes, I can hear you.
Yeah, let me share my screen.
You can see your screen. Please start whenever you're ready.
Yeah. Okay, good afternoon all. We are from team AI SSD, and we will be providing the solution for build-a-thon based on AI ML driven low latency closed loop control. So our team includes 4 members. I myself is Sudev. I work in the domain of deep learning and machine learning. We have Mohit research. He is working on the domain of robotic research. And then we have Dabanko with us. He is from Edge. He works on the domain of edge computing and IoT. And we have our mentor here. He is he has guided us throughout the build-a-thon and help us to provide some useful insights. So starting with, what is a closed loop control for robotic hand and haptic flow? So closed loop control for a robotic hand and haptic glove is used in a scenario where an operator wears a haptic glove in the arm in order to control the robotic hand, which is in a remote location. So what the haptic globe will be doing is giving some commands. It will be going to edge computing infrastructure to the robotic hand, and robotic hand will be doing the same task. And robotic hand, and this thing can be done remotely. So robotic hand, here we are using is a Allegro hand, which is having 16 joints, which is used to estimate the force and pressure which is using to grasp the object. So if the haptic globe is picking a object, then the robotic hand will be emulating the same thing and will be picking the object, and similarly grasp the object. Whichever thing is done by haptic globe is replayed in the robotic hand. So the application of this thing is we can create a closed loop based on many things. For example, telesurgery, remote area installation, etc. Let me go into more details of one of the applications, which is telesurgery. In telesurgery, the doctor is not present in the operation theater, rather the doctor is present remotely, and he is using the haptic gloves remotely to control the operation using the robotic arm which are present in the operation theater. So if we can build a closed loop around this, it will be very helpful, because we will be getting to save a lot of life as well as lot of time. Okay, but here along with it, there come some issues which are high latency, and we are not yet able to achieve human level robustness. So we have identified few issues which are currently in the closed loop scenario. The first issue is the high latency. So as you can see here, the arm is working here, and the arm working here is controlled by the operator, but the receiver uh, receiver's robotic arm is having some latency problems. So the operator have to wait for the feed, then have to give the new command. Imagine same scenario in an operation going on, like you are doing some task, and in between there is a high latency. So it will be leading to a uh, very unimaginable situation, and it makes the life of the patient at risk. So to avoid this, we have to develop some system which is controlling this high latency in the closed loop. And along with it, we will be requiring a professional operator. Doctor won't be comfortable with the haptic hand at first, so it have to learn, which is additional time taking task. And then the sleep detection and crumble detection. So object may tend to sleep, so object may tend to sleep from the hand of the robot. So we have to know if the operator is not informed, and the instrument is dropped off from the robotic arm, then the closed loop won't make any sense, because the task for which the closed loop was created is failing. So we have to also take care of that task is getting uh, is like is getting completed and in a proper manner. So we have formulated, like we have identified this issue, and now we have formulated some problem statement with the help of this issue, and try to solve them. The first problem is self detection and forced estimation. So in this task we have acquired the data of the robotic arm, and have tried to detect the scenarios where the object is getting slipped or getting crumbled due to external, like more force than required, which is applied on the object, which is currently held by the robotic arm. So if we are able to detect this thing, the operator will be notified earlier to take some steps so that sleep can be controlled, because once the haptic feedback is going to the ML model, it will take some more time to go to the operator. But if the ML model can do that thing instead quickly, the operator have little more time, and the latency is reduced a little for the for whole task. And the second problem, which is sub problem of the problem one, is finding the shape of the object. So if we are able to find the shape of the object, we will be able to grasp the object clearly, and we can know what kind of object it is, so we can avoid sleep and sleep or crumble. So in future we will be trying the ML model to have a power, so that the ML model can control the sleep and crumble, and again bring back the model to a stable state. So here is a small example of how sleep is occurring. Like robotic arm is trying to pick up the object, but the grip will be loosening up and the object will be slipping, and that is the scenario we don't want. And same thing will be occurring for crumpling, where the object will be falling off due to high force. It will be just skidding off from the arm and going like falling off to a different place. So we don't want this thing to occur when we are in between a task in a closed loop. So how to detect it? And that is this is for the problem statement two, the detection of the shape. If the shape is fine, the grasp will be a stronger one. So there were some existing approaches which were using sleep detection and crumble detection, but they were using the technology of biometric tactile sensors. So they were not accurate. So for that they have to use other sensors such as for visual information. So which include the cost as well as make the latency high for the closed loop, because they have to give the feedback for multiple sensors. So what we did the advantage of our system is we made a faster processing of feedbacks using our ML model, and we are not much dependent on the sensors. We just use the sensors in the robotic arm, and we also just using the 16 force joint information to predict if it is a sleep or crumble and the shape of the object, and it is very cost effective. And this is the whole solution in the closed loop where our solution will be lying. There is a hectic globe operator is doing some task. For that, the command is given to the Allegro hand or the robotic arm, and there is a feedback like how the robotic arm is performing, and our ML model will be capturing. There is sleep and sleep or crumble. The feedback will be that there is a sleep and crumble, which will be directed toward the operator of the haptic globe, so that the situation can be controlled, and it will be latent, like taking a little time, because the feedback which is directly sent by the Allegro hand are little complex and takes a little more time. So we need to made a ML model in such a way that it will be taking less time. And again, there is one more point is the finding the shape of the object will be giving a good graphs, and I am making the chance of from slipping slow, making the latency controlling the latency, and there won't be any uh, loss of sync between the haptic globes and the Allegro hand. So for the problem statement one, we were for generating the data, we use timestamp data which were generated for each of the event of picking up the object and it getting crumbled or sleeping, and we have just pre-processed it and trained our model. The issue we faced here were like there was event of picking up the object and sleeping, but it was very tough to find that particular instant where the sleeping was occurring, because it was an instantaneous moment where the particular event was occurring, and to identify it was a little bit tougher. And for that we uh, we do is converted the features we received the sensor data to a higher dimension, and after converting using a feature transformer, then use a attendance transformer to convert it into just find the important feature from that, and we were able to get good accuracy. Even the times like the LSTM models we were used to do time series predictions failed here, but our model were behind our model's accuracy, but our model was able to have a good accuracy. And for the second problem statement, it was a easier problem. We have to just find the shape of the object. So here the data set have no timestamps. We have just force information of the joints and corresponding shape of the object, and we just use a simple deep learning model. And from that deep learning model, we were able to get a good accuracy of 99.7%, and the model was only 5 layers deep. We have tried with various more configuration, but it was better. But still, the data size of the models were greater than our purpose model, but our purpose model size was very small, so the latency was controlled very well. When the in testing time, when we run the thing, it was giving a lower latency than the better models, but it was only giving more accuracy of 0.001, but taking around 1.2 seconds more than our model. So we have a small demo of like around 30 seconds of how the things are running in real time scenario. So if you're able to see here, we are when the event of picking up the object is occurring, our machine learning model will be coming into play and try to see if there is a crumble or sleep. So once the object is getting picked, the, the operator will be getting the feed, and it can judge and can control the thing like in a better way. So this was our This is all from our side, and thank you for your time. And if you are having any questions, we are open to questions.
Thank you very much for your presentation. Do any of the judges have questions? Ruth, if I can ask you.
Hi, Moit. Thanks for the very interesting and nice work and presentation. I'm curious about the data you have used. So like it's sleep detection, right? And so like this is more about the object properties. So like how various it was. I guess like for different objects, it might be these effects may be different, and then how much like overfitting is here, maybe like
Yes. So we have used the Allegro hand. It is having 16 joint, and 16 joints. When an object is getting held by a hand, 16 joint exert some force to hold that object, and along with it, it makes certain angle with that object. So we get those two information, and from those two information, we try to see if there it is sufficient to grab the object or not.
yeah, so like object, let's say if it has like different shape, then like these forces on these arms may be different, and then I mean, how generalizable is this to like different objects, I guess, like, and like did you have like very different object types in your data?
Yeah, by seeing our data, we have 13 different objects of different weights, but the shapes were around 5 types. The shapes were a cube, a cuboid, a sphere, a rugby set, and one of the shape is like it is not a random shape, so that it can just grabs it, and we can put it into a class of unknown. For that the thing we have made an unknown class. If the new shapes come, we might classify the shape into that class.
Okay, thanks.
I think we also have a question from Tian.
Hi, thanks for the chance for asking. So I think that's a good presentation. So can you go back to your model architecture page?
Yeah.
Okay. So for your no, I'm saying the DNN model. You just
DNN model.
Yeah. Yes. No, this one. Yeah. So I think this is just a simple DNN network. So compared to 15 layers or 10 layers of the LSTM. So can you just try to justify why this simple model is better than the others? Thank you.
Yeah. So getting the high accuracy, because DNN 15 and DNN 10 were also getting the higher accuracy, but our proposed method, we have run it in the AWS hyperparameter tuner to get the best parameter for the 5 layers. So it was getting now around 99.7, but initially also it used to get around 98.6%, and the rest of the models are just like the standard, like the number of nodes in each of the layers are defined in multiple of like 256 or 512. But for our purpose method, we have used the particular fine tuner to increase accuracy. That's why it is showing more accuracy. But I'm sure it will be 1510 will be showing higher accuracy than our proposed model. But LSTM won't be showing any higher, because to find the correlation, LSTM basically works well on time series data, but there is no relation between first entry and the second entry. So LSTM was not that good here, and like the background for choosing this model was the size of this model. It was much smaller than other models and was performing the same level as the other models were. So we have decided to do that, because one of the model is already a complex model. So we needed a smaller model so that the latency won't be affected in the closed loop. That was the year. That's why we have only run the hyperparameter twinning in for our model only. If I will run the hyperparameter for DNA of 15 layers and 10 layers, it will be giving accuracy more than us, but the latency will be compromised.
Oh, yes, I got that. Thank you.
Okay, well, I'd now like to ask maybe some of the audience members or competing team members. I'd like to take one or two questions if anyone has any. Okay, well, thank you very much for your presentation.
Thank you.
I'd like to next call the team Tech Rangers. Whenever you're ready, please share your screen.
Okay, thank you. Yeah, can you see my screen? Can you see my screen?
Yeah, I can now.
I don't know. I just felt like it. So you want to? Yes. All right.
Can you see it now?
Yes, I can see it.
Okay, thank you. Okay, good afternoon to all the judges, participants, and everyone attending this particular presentation. My name is Emmanuel Ega, a member of the Tech Rangers team, and I've been working on this particular project with Ebedike Frank, Abel Ocha Moses. We've been working on this particular project under the mentorship of Professor James Agajo and Mr. Blessed Buddha. So part of the items we'll be covering in this particular presentation, I'll be taking you through the problem and then the existing solutions, our solutions and the advantage of our solutions. Also be showing you the demo points and results, as well as the gap of the current work. So the problem, we have a high complexity of network management in 5G. That is why we selected a particular use case, which is use case 001 from the autonomous network document. And to solve the lack of domain knowledge base related to the use case, we came up with a design that will help us to deploy components in the network. We also uploaded it to GitHub that can be picked by anyone, cloned, and then work with. So we also use some reference tool sets to come up with to solve this particular problem. So these are some of the problems. We had a problem of high complexity of network management, lack of domain knowledge base related to the use case, deploying components in the network, as well as heavy resource and deployment in the environment. So part of the existing solutions we had manual steps for creating and deploying the components. And the diagram I have to my right is the architecture of the autonomous network. So at this point, we're having the end-to-end network orchestrator. This is the level we are operating on. This is our AN orchestrator. And we are interfacing at the autonomy engine, where we have the evolution controller and the experiment controller and the AN sandbox. So we had manual steps for creating and deploying components, and the domain knowledge was captured in code. And then the third existing solutions we had was we used Python and JupyterLab with a hosted database for a workstation. So these were some of the existing solutions that were there before we came up with our own solutions. Now, our solution automates the process of translating and parsing and also validating the abstracted use case description. So for all the machine learning and artificial intelligence models we have, you will definitely need our solutions to validate, to pass all these particular models you have to ensure that they are working fine. And to test this particular solution, we used a closed loop that imports, exports, optimize knowledge, including structured and unstructured data from various components within and outside of the system. So our solution is very, very important when it comes to validating most of the, if not all, of the use cases, the artificial intelligence models, and what have you. Now, the advantage of our solution is automated. Before that, we had manual steps of processing, translating and parsing use case and description, but our solution has automated all these processes. So we use the use case 001 in the autonomous network documents, which imports, exports, stores, and optimize knowledge independently at a very, very high speed and low latency. And the diagram by my right explains the steps we took to solve this solution. So the first thing we did was we created we queried our Neon4j graphs database, and then we loaded a particular use case database with use case templates, and then we also updated this particular use case templates with notes. We updated this particular use case template with notes, and this is where ROAML comes in. We used a particular Python script called ROAML to load this particular node, and then we also save the template file, and then we loaded the template file to be sure of what we're working on, to validate what we've come up, to validate the use cases that we've loaded to the graph, and then the YAML file we've generated. We use the X opera to validate this particular use case description. So we have a demo video in our repo. You can check that particular video later. And the POC results. We have our use case and templates by my right. These are use case templates which we loaded to the Neo4j, and by the right is the Neo4j database graph, which was generated from our use case templates. Now we queried this particular database. We queried this particular database using our ROAML. We use our ROAML to query this database, and then we have a graph conversion to service templates, and then we're using ROAML, like I said, is a Python package we use to convert this particular graphs into service the service templates, and we validated these templates, which we were able to convert from the graph database to a service template. We validated it using X opera. This is a screenshot of the service YAML template, which we validated using X opera. We also validated this on PyDroid. These are the screenshots there. So for gaps for the current work, we see a situation where we can use human language to come up with network configurations, and we intend to achieve this using artificial intelligence as well as machine learning. So thank you very much for your time. If there's any questions, you can go ahead and ask. Thank you.
Thank you very much for your presentation. Do any of the judges have any questions? Okay, well, I would like to now open up to the floor if any audience members or competing team members have any questions or comments.
Maybe quick comment, Kutnil, thank you so much. Nice presentation, excellent presentation. The Pi Droid that's on a mobile. So you have basically used the two platforms to deploy, right? One on a server and another on a mobile. Am I correct?
Yes, you're very correct, sir.
Okay, great. Do you see any difference in the performance or usability or anything like that? Do you see any difference?
Well, there's a difference in terms of the use. In terms of the use, it's more mobile, and then it's something you can test on the go. You don't really have to have a workstation to really work on this particular use case description. So you can easily pass and validate your use case description on PyDroid.
Okay.
Everyone?
Hello again. From your closed loop system, I can see that your system is able to include some structured data from various components, you say. So have you clearly defined in what cases you need data from other components or in what cases you do not need? Could you please provide more information about this?
Can you come again, please?
Did you hear?
Come again. Can you come again?
Okay, I'm asking again. You said that your closed loop system is able to manage data which is inside or outside of the system. So in some cases, as I can see from your report, in some cases you can gather additional data from various components outside of the system, right? So have you clearly defined in what cases you need such additional data and in what cases you do not need?
Can you hear me?
Yes, I can hear you now.
Can you hear me?
Yes, we can hear you.
Can you hear me?
Mia, maybe I can chat on the chat box, right?
Yes, maybe if you could send
maybe
it
we
right
can go on like that. Okay, thank you.
Yes.
Yeah. I can barely hear you.
So if you could also respond by chat as well.
Okay.
So I'd like to move on to the next presentation. Thank you very much. The next presentation will be on the problem statement depth map estimation in 6G millimeter wave systems. Can I invite 6G Isaac?
Yeah.
To present?
Yeah, thank you. I'll start sharing the screen.
Thank you.
Can you see the screen?
Yes, we can see your screen.
Yeah. Hello, everyone. Hope you enjoyed the presentation so far. I'm Ashwant Reddy from Samsung Research Institute in Bangalore, and our team 6G ISAC has 4 members, myself, Shubham, Avani, and Ashok, and we work on applications that go beyond 5G. To support a large variety of such applications, we need a network that is not just fast, but also flexible, with intelligence to adapt to each of these applications. In this challenge, our goal is to develop a machine learning framework for one of these applications. That is, depth map estimation of environment using 6G communication signals. Integrated Sensing and Communication, or ISAC in short, uses existing communication infrastructure like spectrum, devices, protocol to perform both communication and sensing. There has been a lot of literature in this area where inferences were made on signal distortions to detect location, movement, and even orientation of people and obstacles. The next step envisioned in this direction is creating a digital twin of the physical world. This digital twin can then be used to solve problems like beam selection virtually without ever sending actual beams in the physical environment. On the other hand, creating digital twin using RF signals implies sensing a whole room having hundreds of objects. Therefore, we can no longer rely on the handcrafted features for inferences, as this problem is of higher complexity and scale. We also need to perform extra processing to obtain the multidimensional data from RF signals. Traditionally, this depth map has been done using LiDAR and camera. So we need to train a model with large enough training set with RF signals as input and LiDAR or camera data as ground truth. Thanks to the measurement setup from NIST, which has RF and LiDAR sensors mounted on a robot, we have been provided with the data from multiple locations across a big conference room. Now, moving on to the solution, I'll be handling the first half of the presentation, explaining the problem statement and pre-processing of the RF data before it goes into the ML model. Shubham will then explain the ML model architecture, training, and the results. Let's take a look at the measurement setup. This is the room in which the measurements are taken. We have a transmitter at a fixed location on the left, and the receiver is moving in different areas of the room. Observation of the room changes with the receiver location and orientation. The challenge here is to estimate the depth map of the environment at each receiver position using millimeter wave signals. In other words, we train an ML model that takes MIMO channel response as input and generates dense LiDAR point cloud as output. Note that we are only given channel impulse response as an input. The location and orientation of these nodes are unknown, therefore making the problem more complicated. Now, coming to the outline of the solution, the input RF data has transmission and reception at physically separate locations, also known as bistatic mode, whereas LiDAR sends and receives laser signals from the same location, also known as monostatic mode. So the pre-processing step handles the deterministic aspects of transforming the MIMO channel data, which is in bistatic format, to monostatic format. This makes ML model learning faster and more understandable. Looking at the input data at each location, we observed that RF data has lower resolution and fewer reflections, whereas LiDAR has both higher resolution and larger points of reflection. So at each RX location, we transform bistatic RF data into monostatic format and train the ML model by fitting it to similarly structured LiDAR ground truth. The first step in pre-processing is to perform spatial transform of the input channel response. This is done so that we can transform our data from antenna space to angular beam space. This spatial transform therefore helps us to get to sensing framework from communication framework. On the right, you have a plot of the matrix H-beam for a single delay, where each entry represents power for an angle of arrival, angle of delay pair. The matrix H-beam gives us power of reflections at points separated in distance by 17 centimeters and on average in angle by 22.5 degrees across azimuth and elevation. Now that we got H-beam, we need to transform it into monostatic format. That is, as if transmission and reception occurs at RX or at a receiver. The first step in this transformation is to find the line of sight or LOS path. To find the LOS, we select beam which has higher power, lower delay, and tighter beam width. Since the line of sight path doesn't have any information about the environment, we remove these entries from H-beam. But we store the line of sight path parameters as they give location and orientation information of the receiver, which will be used in subsequent steps. Next, we remove the effect of transmitter in the matrix H-beam to get power map from RX perspective. We do this by projecting AOD dimension to delay dimension. The signal shown here travels R1 plus R2 distance from RX from transmitter to receiver. So we need to shift the delay of this entry in H-beam from R1 plus R2 to R1 so that it appears to arrive at a receiver directly from the reflection point. So we need to calculate the ratio R1 by R2. In this triangle made from the line of sight path and the current reflection, the delta AOD is the difference between an angle of departure of line of sight and of the current reflection. Delta AOA can be defined similarly. Here, we use line of sight parameters saved in the previous step. Applying sine theorem to this triangle, we obtain the ratio R2 by R1 as ratio of sines of delta AOA and delta AOD. Now we can project the entries in AOD dimension to appropriate delay to get the power map from RX perspective. In conclusion, we remove the effect of TX or transmitter by projecting AOD dimension to delay dimension. The last remaining step is to scale the power so that the reflections appear to travel the receive path twice. So we multiply it with R1 by R2 square. With this, we have finished the pre-processing step where we have taken the channel impulse response in bistatic format and obtained RX power, which is in monostatic format, similar to LiDAR as output. Now it's ready to be sent to the ML model. The plot shows the pre-processed data for a single RX solution. We see power at RX across 64 different angle of arrivals and 100 delays in each of the AOA. Shubham will now explain the ML model and this.
Thank you, Yashwant, for covering the pre-processing part. So, so far we processed the input CIR data, which and obtained the power of reflections at the receiver from 64 directions and 100 points in each of the direction. This is the input for the ML model. Now I will explain the output for the ML model. So given output for the challenge is LiDAR PCD of the room as seen by the receiver. For the ML model training, input and output data is given for across the location, across multiple locations across the room. Perception of the room as seen by the receiver changes with the receiver location and orientation. And here are some snapshots explaining this behavior. Assuming RX is at the origin, we observed across the location LiDAR point are inside of this bounding box, which has minimum bound of -16, -16, -2, and max bound of 16, 16, 2. So we use a voxel grid as the output for the ML model with the minimum and maximum bound as these. With the voxel size of 0.25 meter, the dimension of the voxel grid is 128 by 16. If we use a higher voxel size, the dimension will be reduced by 8. Note that higher the voxel size, complexity of the model will be lower, but the resolution of the output will also be lower. So there is a trade-off. Now, why this problem is so challenging to solve? There have been enough research on the camera as input and LiDAR as output. There has also been few works on high resolution LiDAR as input and radio signal as the output. But here in this problem, we have a more challenging situation where RF data, which has way less resolution than the output LiDAR data in terms of range and angle, because the LiDAR is at higher frequency and guided by the laser beams, while the RF sensing is limited by the sampling rate and number of antennas. LiDAR gives more reflection compared to RF sensor. Here, the input dimension is quite also lower, 6400 compared to 2,62,000 voxels compared to output, which is around 3%. Apart from this, in this challenge, we also do not know the TX and RX locations. Moving to the ML model. So the pre-processed CIR, channel impulse response, which is monostatic RX power, is fed to dense layer, followed by the upsampling layer and further CNN layers to predict the voxel grid and further point cloud data. We use upsampling layer because input to output dimension is around 3%. And we use CNN layers because the correlation of the reflections exists in the neighborhood. Now coming to the training parameters, we use custom loss function, which is similar to the binary cross entropy loss function with added weights for the label 1 and label 0, where label 1 get higher weightage compared to label 0. Because in the voxel grid, most of the voxels are 0 and only 13K out of 128 by 16 voxels are 1. We train the model with 3,400 samples for the training across these areas, these locations, and we test the model with these 529 locations across this testing area. We train the model with Adam optimizer with decaying rate of 0.0005. Here are some snapshots of the actual LiDAR PCD and the predicted PCD. We can observe from this plot the ML model proposed returns LiDAR like high resolution point cloud, and also along with this change in the perception across the location and the orientation is nicely captured in this predicted PCD, even though the TX and RX location is unknown. Now we have explained the quality of the, as we have seen the quality of the prediction, given the difficulty of the challenge, now we explain the quantitative evaluation metric for the challenge. So here the camphor distance is used for the evaluation. Camphor distance measured the discrepancies between the point cloud and return how close the 2 point cloud are. Lower the camphor distance, closer or similar they will be. Now in this slide, I'll explain the error analysis done in terms of camphor distance. We have plotted the camphor distance for the testing data, which is collected across this purple colored area in the room. The transmitter location is at the bottom left corner. Here, the blue means the camphor distance of 1 meter square, while the red means the camphor distance of 9 meters square. We see the most of the samples are blue, which suggests the prediction is good for the room of dimension 16 by 16 by 4 meter cube. We also observe in this figure the camper distance across the location of the testing data is around 2 meter square. While the samples which are closer to the transmitter, the camper distance comes out to be 1 meter square. We also did error analysis on the training data and find out the training area is along the blue route. We found out for the voxel size 0.25 meter, the camper distance comes around 1.5 meter square compared to the camper distance which is 2.2 meter square for the voxel size of 0.5 meter. So that's why we use 0.25 meter in this proposed algorithm as a voxel size. At last, we summarize the observation. The ML model proposed returns lidar-like high-resolution point cloud. Change in the perception of the room across the location is also nicely captured in the predictions. Average camper distance comes out to be 2 meters square, which is good for the room size of 16 meter by 16 meter by 4 meter. Average camper distance is 1 meter square for the samples which are closer to the TX. And finally, the future works. The future work include a training with the high resolution input and also the high resolution output in the ML model with lowering the voxel size. We will also experiment with including all the locations as the input for the ML model, and also we will be using the TX perspective along with the RX perspective. Thank you for listening. Any questions?
Thank you very much for your presentation. Can I ask Dr. Madi to ask your first question?
Yes, thank you very much for this interesting presentation. I am wondering if generalizability is an issue in this problem statement. Is the train and test data from the same environment? And also, what about the SNR for the RF data? Have you studied effects of the SNR as well? Thank you.
Thank you for the question. We assume so the training and testing has been done. Let me just go to the slide. These are the training samples. So the area marked as 1 and 3 are the locations which we take as training, and the area with purple lining is the testing samples. So the SNR, the data provided to us from NIST had they collected it at a very high SNR, like at least 60 dB. So this whole analysis assumes a very clean input RF data. But still the multipath and other artifacts are still there. So,
yes, what is the frequency for the measurements?
The frequency is 60 gigahertz.
Okay. So it's mostly line of sight. I believe line of sight is the dominant case at that frequency.
There are multipath components also. Basically, I guess this goes a little deeper into the actual measurement setup they have. So the transmitter and the receiver both have circular horn antennas, which are circularly separated, and all of them transmit. So basically, we are broadcasting it out. And they measure the channel from each horn antenna on the TX to each horn antenna on RX. So we do capture multipath components.
Okay.
So, and also multipath capture is also necessary for the problem, because that's how we get to plot the depth map of the room.
As I explained in one of the slides, LOS doesn't actually have any information corresponding to the environment. So we actually remove the LOS information before going into the ML model. So so we do have the multipath components.
Thanks.
Thank you very much, Professor Adachi. Can I ask you to unmute?
Thank you for a nice presentation and impressive results. I have 2 questions. The first question is does the orientation of the antenna have any impact on the accuracy of your system? And the second question is related to the first question. how is the generalization? For example, like please go back to the second last slide. Okay, next now, maybe next. Ah, okay, sorry, the previous one.
Yeah. Yeah.
Yes, this one. Okay, thank you. So in this setup, the testing sample is within the training course. The testing course is inside of the training. So what will happen if the testing is outside of this training course? For example, like just right side a little bit. I mean, a little bit farther from the TX.
Yeah, so one thing I want to add is that the area 2, as you can see, the 2 rectangles around area 2 are tables and chairs. So there are obstacles which are very specific to area 2, even though it lies inside the area 1 rectangle. So the environment that area 2 sees is completely different from what environment area 1 sees. So so you can say that it's like completely different environment. So yeah.
Okay, I see. Thank you. Okay, how about the first question? How about the orientation of the antenna?
So they do matter a lot. So so can you repeat the question?
I mean, because you are talking, you are using the millimeter wave, right? And also the 64 antennas at the transmitter side and the receiver side both. Then in that case, I'm just wondering that is there any issue about the orientation of the TXLX antennas, whether they are facing or they are misaligned or something?
Yeah. So our solution is independent of the what do you say? We assume that we do not know the orientations and continue with the problem. So we have to figure out the orientations and then estimate the depth map accordingly. So that is also a part of the problem. So does that answer the yeah?
Yeah. Okay. Thank you.
So this is Blandino from NIST. I wanted to add one point on the generalization question and the fact that area 2 is kind of partially overlapping area 1. So what has been said is true. So the environment observed is kind of different because there are table and chairs and all. But in the if you look at the overlapping section, the overlapping segment, there is actually a very big difference in orientation because, yeah, I don't have the pointer, but the receiver is mounted on a robot and is basically circling this path, and the orientation on the overlapping section is different. So while they are in the same position, the observation are actually different. So we designed the challenge in this way. That is kind of a first step of generalization, because actually the testing data are never the same as the training data. It's still the same location, but I think it's kind of the first step towards a complete generalization, for example, testing on another environment. And if you have, I heard other questions on the antenna and the data set collection. If you have questions, you can contact us at NIST.
Thank you.
Excuse me, may I ask a question? So my understanding was that there is some beam swiping in collecting the data. Am I correct, or is?
Yes, that's correct.
Oh, okay. Okay.
It's basically what we do is to sample the channel at each antenna, but it's very fast. So it's like in the order of milliseconds. So you can assume that it's kind of collected at the same time, and then we perform some kind of calibration offline. We perform beamforming, calibration of the hardware, and we obtain very high resolution RF.
Okay, thank you very much.
Okay, if there are no more questions, I would like to go into our break. Thank you very much for your presentation.
Thank you. Thank you, Steve.
So we will be taking a break until 2:30. If you could all come back before then. Thank you. We are going to now start on our presentations for the problem statement location estimation using RSSI of wireless LAN in an NLOS environment. The first team to be presenting is Tele AI Lab. I ask you to share your screen, please.
Okay. Hi there, I'm Mingjie Liao from Tele AI Lab. It's my great honor to be here to give a brief introduction of our work on RSSI-based location estimation. And in this work, we use multitask learning method. And after a short background, the talk will be divided into these 4 parts. Okay, so it is well known that the global positioning system, GPS, is widely used for outdoor location. The GPS requires line of sight, which means that there is no obstacles along the propagation path of radio frequency, and it is hardly satisfied by the indoor location. However, the indoor location-based service, such as smart retail, smart home, is promising. Hence, signals such as Bluetooth, received signal strength are widely studied for indoor location estimation. So in this competition, we are given 4 locations of 4 access points, and the locations of the training points along with the RSSI. And the environmental information loss and loss is also given. The task is to estimate the positions of the verification points with given RSSI referring to certain access points. So it is well studied that the RSSI is related to the distance. So in the left-hand side, they are triangular or trilateration method, which further decompose the distance into coordinates or positions. And on the right-hand side, Wi-Fi fingerprinting method is carried out in 2 phases. A survey to collect RSSI of reference points to fulfill the query by comparing RSSIs of target points with reference points. However, in our situation, the distribution of the points are somehow sparse, and there are certain gaps between verification and the trailing points. Hence, we turn to the distance decomposition scope. Several models describe the relationship between the RSSI and distance. They describe that the RSSI is some kind of linear to the logarithm of the distance with a base 10. Moreover, the environmental information loss or N loss can be introduced into the measured distance through a bias term BI here. So these theoretical studies support that our proposed method can fully use the data given. So our solution includes 3 key steps. The major steps is the modeling. We select 3 tree models as the baseline, and we put forward the multitask learning model. The multitask learning model estimates latitude and longitude in one model. In this way, it can better extract useful features from the input to improve the performance. And the performance are evaluated by the mean error and the maximum error in meters. To begin with, first we remove the columns, number, and channels from the dataset since they offer little information, and also remove the duplicated samples. It seems that within the dataset, there's little dynamical fluctuations, so we treat the model in a static way. In the triangulation or distance decomposed methodology, 3 or more APs can estimate the positions of one point. Hence, we simply concatenate the data carried by APs to form an input sample. In practice, the order of APs in the sample does not affect the results. However, as the structured data, the order matters, such as the sample number 0, the order is 1, 2, 3, and the second sample here is 1, 3, 2. They carried exactly the same data. However, they can be regarded as 2 different samples. So by permuting the order of the access points, we increase the number of available samples. Then we feed the augmented samples into the tree models. We would like to emphasize that one tree model can return only one estimate, either latitude or longitude. Hence, at least 2 models are required to predict latitude and longitude. We use neural networks to realize the multitask learning. The architectures are shown on the slide. The main ideas behind is that we use the shared layer to extract RSSI distance relationships followed by two specific towers to extract the distance latitude and distance longitude relations, respectively. In this way, the model can estimate latitude and longitude in one model. So by this architecture, we can better extract useful features from the input samples to improve the performance. So our multitask learning model obtained the best results measured by the mean error. However, the maximum error is poor. But we investigate the distribution of the errors given by the multitask learning model. It scrolls to the left, the smaller error zoom. So it somehow shows the potential of the multitask learning. So to sum up a bit, we apply the multitask learning to the RSSI-based location estimation. The multitask learning model contains shared layers and specific towers, which can learn multiple tasks in one model to improve performance. So these models lead us to a good ranking in the first phase stage. So in our recent work, the RSSI distance relations are studied in a pure data-driven way. However, we think that by introducing the a priori knowledge, namely explicit usage of the loss and loss environmental information may probably improve the performance. And if possible, we would like to study the spatial and temporal dependencies simultaneously to see how it works in this problem. And since we are embracing the 6th generation, accurate positioning, accurate location estimation is essential for integrated sensing and communication. So that's all for my talk. Thanks for listening.
Thank you very much for your presentation. Can I ask if any of the judges have any questions? If you could open up your mic, please.
Yeah, hi, thanks, ma'am. Munje, thank you for the nice presentation. So as far as I don't know too much, but like there's been some work on this RSSI-based localization in the literature, right? Like how would you put like your work compared to the literature? Like, are you aware like how original, like what is different to the existing work?
Okay, so do you mean what's the difference between the multitask learning to the theoretical studies?
I mean, like there's been some studies, right? So like the main difference with your work and the studies is it the multitask learning essentially?
Yes. Okay, so the theoretical study only studies the relations between the ISSI and the distance, and they use this model to estimate the distance, and then further decompose the distance. Further decompose the distance to estimate the positions. However, there are some baseline models we tried. There are 3 models, but the tree is only one tree model only predict one latitude or longitude. The tree model can predict latitude or longitude respectively, and the multitask learning model it is the one model to estimate longitude and latitude at the same time, and I think intuitively there are implicit relationship between latitude and longitude, and so these shared layers can better extract these information. And the traditional tree models they directly extract the relationship between the ISSI to the latitude or longitude. But from the theoretical study, we think that the distance can be a bridge to cover the gap between in between to improve the performance.
Just one more question, just seeing this figure, like what if the last layer was also shared, like, and then your essentially output would be like latitude, longitude as a vector, like, would that be different?
Sorry,
not like a multitask, but like what if this was like a single task, you know? So like you have these separate layers, right, at the final layer for latitude and longitude. Like if they were joined, like would anything change?
Okay, well, we didn't use the neural network for a single task model, but according to my experience using multitask model, there is the paradox called Stan's paradox offered by a mathematician in Stanford. It says that in the multi-Gaussian distribution problem to learn the joint distribution together can beat the thing to learn the single distribution of one features. So I think this is the the theoretical support, but we don't explicitly try to build a single task model.
I see. Okay, thanks. Good work.
Thank you.
Do we have any more questions? I'd like to open up the floor to other audience members or competing team members if anyone has any questions. Well, I have a question myself. I'm not really sure if you mentioned it, but you said that you find potential in multitask learning. Do you have any idea how you can possibly reduce the maximum error that we see here in this graph?
Oh, okay. So in this case, of course, since we use the neural networks, so there are more parameters. So the parameters must be more than the simple model or the tree models. So one way to improve the performance is definitely with more data. And the other way is since we have only two since we have only 2 tasks here, so in my opinion, if we can introduce more tasks like to predict the loss or unlost environmental information, maybe more tasks can help to better extract information to reduce the maximum error. But however, in this case, we didn't use more tasks because in the data set there are only 4 points that has unlost environment.
Okay, thank you very much.
Thank you.
Does anyone else have any more questions or comments? Okay, well, thank you very much for your presentation.
Thank you.
I'd like to move on to the next team now, Git Labs. If you could share your screen, please.
Yes, can you hear me?
Yes, we can.
Okay, so my name is Zhou Xiaohan, and we're from Git Labs, the Kyushu Institute of Technology, and I will give a presentation about the task of allocation estimation using SSI of wireless line in in-loss environments. So first, a brief statement of the task. There are 4 access points in the location area, and we have to estimate the location of 13 targets inside the area by RSSI values of those access points, which is difficult, and not to mention that when obstacles are added to the area. So in this task, we use AI ML tools to improve the accuracy of the location estimation. And the next is our consideration of the task. To estimate the location, the trilateral positioning method is always effective if we want to measure the position of the targets. And we know at least 3 distances between the targets and the other 3 stationary place we set in this, which is in this task is those access points. And the estimation area 40 meters multiplied 35 meters. The trilateral positioning is quite accurate in this task. So if the distance data is adequate and precise, however, we don't know about the distance data. In fact, our SSI values is directly related to the distance. The further distance is, the smaller the RSSI value is. And because it's always negative, we use absolute values for making it easier to calculate. In conclusion, if we can get the distance corresponding to each RSSI value, we acquire the complete data of RSS distance, RSSI and the distance, and the problem we've solved. In the training sample, all given RSSI data are integers and belong to 45 to 80. And those over 80 can be considered to error or because of obstacles, and we will talk about this later. We decide to use KNN, K nearest neighbor model to predict the distance data which are not provided. For example, when we need distance data of RSSI value of 62, which we don't have, but we do have data of 61, 64, and 65, it's possible to predict the data of 62 with those near data. So we counted all the samples and we got the data. For the RSSI, for example, the RSSI of 61, there are 3 different distances, and we couldn't know which one is correct, but we could use the average of 3 numbers, or even more, 5 numbers. And those 5 numbers are K values in KNN. So if we find the optimal K, we get the right data, and we say we get the closest one to the correct values. So we plan to use KNN to complete this chart, use nearest K numbers to predict one, and training to get optimal K for every RSSI value, searching K from 1 to 10. There will be 10 to 36 power iterations. So unfortunately, we don't have enough time, so we reduced the iterations, and as a result, if the RSSI is 60 to 69, the K value will be 5, and in other data, K value is 2. So as for the solutions of the obstacles, by analyzing the training sample, we found at least 3 obstacles through the RSS data of access point 2, 3, and 4. So for example, when one RSSI value is very high, the target might be behind of the obstacles. Then other 2 RSSI values can help judge the reason that abnormal high RSSI value is because of obstacles or just a long distance. And so in these pictures, for example, there's one situation that if the target is about this place and the obstacles is red, so if so we couldn't find the right place of the targets because the data is just the same to the blue points. But anyway, when the conditions are met, there are obstacles between the targets and the certain access points. We use fixed distance under these circumstances in trilateral positioning, and there will be 3 different situations written here. And the next, by using KNN model, we get a sketches result, but clearly it's not the best. And it's just some scatters around the actual curve, while what we really want is a smooth curve like the red one. So we could use another tool to predict the more accurate results, and it becomes a nonlinear regression problem. So we decide to use DNN with gradient descent algorithm. The results of KNN RSSI, KNN to RSSI distance as inputs. By changing the distance of each RSSI, we can find the local extreme of the average error for each RSSI and do the iterations. After 200 iterations, we got results. So as to the verification data sets, there are also 13 targets in the location area, and the results without DNN, just KN, the average error is about 50 meters and maximum error 24 meters. So by using DNN, the average error is reduced a little, 14 meters, but the maximum error is clearly reduced. So this is the result we got, and in the conclusion of the discussion, the step change of the gradient descent wasn't set. If we set that, that could improve the results even more. And we only find one of the local extreme. Maybe there's other values that could make the error smaller. So this is the jobs we haven't done. And that will be all. Thanks for watching.
Thank you very much for your presentation.
Hi, good afternoon. So first of all, I would like to thank the ITU organizers for the conduct of the event. And today the title for the presentation is on multi-loss function to improve the test detection and segmentation. And the problem statement is slide transition detection and title extraction in lecture videos. So we are the team member of 2 people, and our team name is AI Vision. So myself, Anuj Abraham, and I'm a senior researcher at Technological Innovation Institute in UAE. And my friend Shikala Prasad, he's working as a scientist too in Agency for Science, Technology and Research in Singapore. So I was an ex-employee of A-Star, and where we started this work. So the presentation outline will be like I'll be giving a small introduction into the problem overview of what the problem statement is of, and what motivated us to this work. And then the key contribution to this particular problem statement and what we are proposing and how we have handled the data set, and some results, simulation results in terms of comparative results with the baseline work, and some ablation studies in terms of computation cost and FN score and other metrics, and finally the concluding remarks and the scope of future works. Okay, so in this current task, we need to address two different problems. Like one is on the detection side and one is on the segmentation of the titles, for which we have a joint learning concept. So mostly you might have seen in YouTube's video chapter, where the feature segments of a video like is divided into sections and it is marked by timestamps, and then we can based on the interest of the viewer, you can navigate to the particular section of the video. So in this video, in this image, you can see on the bottom side there is different timestamps, and when the cursor is moved to the timestamp, you can see the title of that particular video being running. So this is just by clicking or pressing the chapter marker and by selecting the timestamp of the video description. So this is the problem statement which was given, and already the ground truth and the data video files were given to us, and we need to improve from the baseline work. And for this, we have used a classroom loss function approach. So this is nothing but which is similar to our classroom in schools. So where the students are learning the same information or the concepts, but in different perspectives or in different ways. So based on the students' capabilities, and then we assume that the best among them represents the whole classroom learning performance. So our algorithm is also designed in such a way. So in case if the concept is not clear to any of the students, then the teacher improvises this explanation to many students and makes them to understand the concept. So in view of this, the same functionality of our proposed classroom losses, where the minimum loss out of multiple dedicated are used for the feedback, and then update the model's weight, which then boosts up the so that is the one thing. And in the problem statement, what is given from the ITU, the challenge for us is to create an AI model which annotates the slide transition by first one is for identifying the starting and ending frames of each slides, which is shown in the video. Then we need to extract the titles of each slides, and all these videos are recorded at 25 frames per second, the slide frames. And the data set was collected by the challenge, and we downloaded them and used them for processing a solution to improve the baseline performance. So the details are like the video files is covering the presentation from the speaker start screen and the share right to the moment, and then it is turned off. When it is turned off, so all those information are there, and the video files are of different length, and which is in minutes, or and the resolution is also different. And we are also being provided a ground data set which is of 2,500 slides transition, which is showing the starting and ending frame of each slides, including the titles. So that was the data set which is given from the ITU side. And this slide represents the slide annotation. So while we understood that this is a slide annotation problem, the dataset contains some complex features. So the cases of the presenters demonstrating the real world footage, or the minimizing the PowerPoint, or another programming getting open. So these are all treated as a non-slide content. So to distinguish them, the content from the everything else, in prediction, we utilize the each slide column. So if it is set to 0, it is mean that any of the video fragment that is not a slide, and it is 1 for the other cases. So if it is the representation of the frames is extracted from a screen share of 25 frames per second, and this is what illustrated in this figure. So also in the figure on the downside, you can see the ground truth which is available for the videos. So in the ground truth, the structural information is something like you can see on the row 1, the starting frame 1 to 2, which represents the range of possible starting frame numbers. Then we have the end frames 1 and 2. So this is a range of possible ending frames of these of the slide. Similarly, there are title 1, 2, 3, and 4. So this is all representing one or more optional slides, titles of the slide. Then there is also another bonus slides, is 1 and 2. Which is for the bonus answers, like a solution will be granted double points for predicting this slide, and a solution is granted double points for predicting both the slides or something like that. So these are optional types, and we also have a hybrid slide case also is hybrid. So if it is labeled as 1 and it is an optional prediction, and the hybrid slide will be a part of the prediction output, it will not be considered as a mistake, or it will them into enhancing your training. So we were being motivated to this particular work from the paper from the same team members for this work, which is from the Prasad, the paper which is highlighted there. So they have in this paper we have introduced a multi-laws view invariant stochastic prototype for embedding to minimize and improve the 3D recognition of the objects, and using the multi-laws learning approach. And this was been published in IEEE processing letters in 2021. And as I mentioned in the introduction, we also used a classroom learning approach. This was also published in the Computer Journal in 2022. So in both this paper, it was more focusing on the 3D object recognition, and the future work was given for open scope for the title detection and segmentation. So we have attempted for this particular problem the multi-laws in detection and segmentation phases. So the proposed solution we have on the data set, the data feature extractions, and the traditional single laws. And from a proposed one, it is the multi-laws. So the proposed solution is based on modifying the learning strategy and development of multi-laws function to improve the text detection and segmentation. So the basic block diagram, as you see here, we are not in this work, we are not modifying the deep feature extractor block. This is the same which is used in the baseline work, which is provided by the organizers. And but we are aware that in literature it is seen that complex architecture models will be better results in extensive results in the will be extensive computational course. So our focus will be on the learning strategy, like improving the loss function in terms of all those improvements. So hence, for focus for such a result, we use where the deep models are trained using simple objective multi-loss functions as similar to simple loss functions. So how we handle the data, the steps involved is since the challenge has videos as an input source, we need to extract the frames from each video files to feed into the deep model. So the following steps were we have taken. And the video frames in the baseline was 25 frames per second in the ground truth data. So we also used the video frame per second is 25, and use the video files to extract images for this. And suppose, as I said, the videos are of different varying length. So we have a different total size of the images for particular data sets. We had a section of 16 folders of data sets. So this is just one instant we are given for one folder data set, where suppose the length is 20 minutes, then 20 minutes into 16 to 25, which means we have around 30,000 slides, which contains no slide, title, slide, and new slide, duplication slides, all those things. So so that is how we have categorized. There are three types of images, which is no title, same title, and new title slides. And once these images are extracted, then they are categorized into the training and validation set. So as you see in the ground truth information structure, we have extracted the number of frames with the same titles by using the starting and the ending frame numbers. So here in this ground truth CSV, you can see, suppose in the case of the ending frame is 219 and the starting frame 2 is 35. Sorry. Yeah. So for the training set, if you see 219 minus 35 will be a total of 184 frames will be there, and out of that we used 80-20 training validation test. So training will be 147, and out of this 37 will be used for validation. So similarly for the different instance for the other title extracted video files we have seen. So using the frame number, we split the data set, and the splitting is computed based on the frame number by 80 by 20, and we extracted the number of frames with the same title by using the starting and the ending frame numbers. So once this process is done, then our main task is to detect the title from the slides. So we have the baseline of ground truth data set with titles. So there were no titles. Without titles, the slides were not available in ground data. So hence we have extracted the frames from these video files, which was provided from organizers, and for feeding into the deep model with title and no title slides as shown in this figure below. So we can see that on an average, we assume that the titles are on the top of the each slide frames. So from each slide frame, we assume 1/3 of the portion will be representing the probability of title search, and that is used for training. So the remaining 2/3 represents the no slide, and this is what shown. And the red line which you see on this figure will be the threshold for the title search. So above the threshold, 1/3 will be for the title, and below 1 will be for the no title case. So using this concept, we have mask and for the distribution them like for white color for 1 and black for 0. So with a threshold for each title line represented in red color there. So rather than annotation, we create a mask which are very easy to implement. So yeah, and this is a basic BGG convolution classical CNN network, and the network what it is used is Deep Lab V3 with the custom head for the prediction. So in our work also we use the same architecture which is given from the baseline. So we didn't touch the architecture side. We just gave the input to that one in terms of loss functions and applied our algorithm to it. So the basic work from we use is Deep Lab V3 ResNet 101, and which is the backbone of the network. And there is no changes to the architecture side we have done. And we have observed the negligible model computation cost, which is more equivalent to the original. And the multi-loss training strategy converges the network much faster. And another advantage we found is the significant boost in the performance by around 5%. So when we come to the comparisons for the baseline, and we used 4-layer for the multi-loss, 4 functions for them, and the number of epoch iterations is 10, and the F1 score when we compared with the baseline, we got an improvement of 0.182, and for the AUROC, which is the accuracy curve for the area under the curve, and that also we also got the improvement. And the type of loss functions we used is mean absolute error, mean square error, mean squared logarithmic error, and the variation of Huber loss functions in our experiments. So some of the ablation study for the baseline with the 2 losses, 3 losses functions, and 4 losses functions. So we have compared our methods with several settings, which is mentioned below for the F1 score and the AUROC. So the first experiment is to show the multi-loss concept. It actually helps in the network boost the performance without much computation overhead. So this figure shows that the bar graph for comparison of several loss functions. As we see that multi-loss function for 4 students, performance outperforms the baseline method by roughly around 5%, and which is really a significant number. And that means that there are different losses that can recognize the different title captions at different times of the feature representation. And this learning strategy actually reduces the computational cost also. So if you see the ablation study, the improvement of the test accuracy is like around 1.9, and the AOROC is with the AOR test F1 accuracy is the F1 score is 5.2 improvement, and the AOROC is 1.9%. And in terms of computation, also we have plotted the bar graph. Means that the different losses have recognized the different title captions for the learning strategy, which actually reduces the computational cost. And instead of several epochs, our model converges much faster. The cost cut is roughly around 37.2% as shown in this figure. So 68, if you assume that 100% is used by the baseline, and for now for proposed work, the computational cost calculation is around 62.8, which means the 37.2 is a cost cut, which is roughly in our work. So the basic scores, what we are taking into consideration is F1 score, which is a measure of test accuracy, and the other one is on the AUROC, which is a cost difference of the accuracy between the ROC curve for the baseline and the proposed. So from the to conclude, in this work we have proposed a multi-loss based progressive multi-view learning approach for segmentation and prediction, and the proposed method boosts the network learning capability and converges much faster with a significant improvement. Our work also enhances the learning power of the existing model by adding without adding any changes in the network architecture. So we use the classroom learning which inherits the several loss functions as their students and learn the same feature representation, and it is used for the bus student to compute the backpropagation gradient. And the classroom learning approach consistently outperforms the state of the art. And with the help of the proposed four loss function, a computational cost of 62.8%, resulting of 37.2% computational cost from the baseline work. And the gradient calculation is optimized for the detection and segmentation. And for the future scope of the work, we would like to further optimize the learning curve with minimal number of learning parameters. And also we would like to extend our work to the concept also be used in optimizing the multi-view representations. So thank you for your attention, and if you have any questions, I can address.
Thank you very much for your presentation. Do any of the judges have any questions? Okay. Do any of the audience members have any questions or comments? Thomas, please.
Okay, there's a question in the chat, so maybe they can answer the first one. Have you used original test set to estimate F1 score?
Have we used original test set to estimate the? Yeah, so whatever I was telling about the training and testing, the testing refers to the validation. So it is a validation set what we have considered. We have used our own distribution for training and validation. And whatever I mentioned for testing is meant for the validation, and that is used for the estimation of calculation of the F1 score.
Okay, thank you.
Okay, so in the current implementation, right, you just if I understand correctly, you just take the baseline as it is without changing. Okay, by changing only the loss function. Why didn't you do further improvements, or why did you consider that the loss function is the only important aspect from the baseline?
Okay, so as I mentioned in the motivation slide, like we already have some multi-loss function we propose for object recognition. So we understand that using the same concept for prediction as well as for the segmentation and title extraction, it will be helpful without any giving additional burden to the architecture. So that's why we use same deep feature architecture, and instead of using the single loss function or the single loss function which is there in the baseline, we thought of using the multiple loss function and use the learning strategy like in the classroom. So whichever is above, we keep a threshold like 90% of confidence, and if a student crosses more than 90% of confidence, and then we need not train the all the other students like we can skip some iterations in that case. So which means the best students confidence can be used for the other students updations. So this was a main criteria which we have used in the learning algorithm, and which gives us significant improvement in terms of the F1 score and the area under the curve for the accuracy. Is that fine?
Yes, that's good. Thank you very much. Maybe a follow-up in terms of, do you think by changing the architecture itself from the baseline, maybe a new architecture or different architecture would improve
even
on the...
in the baseline it was used ResNet 101. We have also changed with the ResNet 18 and 54, and we could see that the computational cost is like maybe it is lower, but it is increasing. But it depends on, and we also tried with the different loss functions also, like the other loss functions are available for the regressor for getting the precise bounding box. So all those things also we have considered in this case, and we also tried with, we restricted with 4 loss functions. More than 4 also we tried, but there is no point in using 10 or 100 loss functions. So we should understand the data set, and for that particular data set we have to create our own loss functions and then use that one. So which gives a significant improvement. So for different data set, different loss functions can be used, and different multiple types can also be encountered in that case.
Okay, Vishnu, if you could open up your mic, please.
Yeah, thank you. Yeah, I think first of all, nice presentation, Anuj and colleagues.
Yep,
the just basic question, maybe I missed it. The results are for which problem, which part of the problem? Is it for the, I suspect it is for the title, no? Or is it frame?
It is for the title.
Okay, so I suppose, I mean, we did not think of it like this. It's a nice perspective. It appears that you have actually extracted the title first and look at the frame, or rather the similarity in the titles. It appears to me like that. No, so basically, are you looking at the first problem at all, the frame delimiter?
We can enhance this one by considering the other parameters also, like the title. We can also see the footer, the header, and if you have any other features which needs to be extracted, those information also can. So this, as a basic work, we have done as a title extraction for this segmentation.
Cool. No, it's quite interesting. Yeah, I mean, again, it is quite surprising and interesting. This, can I ask you about your data extraction? I think you had one slide on that. That's interesting as well. So, can I ask you how much involved was this? Just curious. So, how much of extracted data did you get, and how much of processing and resources did you need to do this?
Yeah, so that is actually ResNet will be using some 60 million parameters in their architecture model. So we have actually used like 2,500 ground truth slides, which is given from them. And then we have extracted from the videos, like for each dataset file, we had around 60,000 slides, and we need to categorize like which one is to be used for the training and which one for the validation. And so because then we took the average of all the 16, we had 16 folders, and in each folder we had around around how many, like 100 videos from the community researchers. So we took the average of all to calculate the scores of this. And for using this, we have run in NVIDIA GeForce 1080 Ti GPUs. The batch size what we consider is 4 images, and 2 images will be sent to 2 GPUs, and which has a RAM of around 11 GB. And then we used train the model weight size will be around 235 MB for each.
Very nice. Yes, thanks. Thank you for that comprehensive answer. Yeah, thank you.
Yeah, thank you.
Thank you very much for your presentation. I'd like to move on to the last presentation of today for the problem statement, synthetic observability, data generation using GANs. And I invite CMRI AI Quants to share their screen and start the presentation, please.
Can you see my slides?
Yes, we can.
Okay, so this will be the last slides, but not least, I hope so. So today I will just want to introduce our solution for the synthetic workload data generation using GANs. Our team comes from Beijing Quantum Evolution Company and the China Nobel Research Institute. So the basic problem is come from the cloud workload data, and we know it's extensive use in business, but limited availability. And we get the data, the origin data set, have the memory, CPU, load, and the network data set. And the problem is to try to just solve this availability issue. So train the GAN model to generate synthetic data. Moreover, we can simulate a synthetic workload data in many scenarios. So just we have 3 steps to solve this problem. So first is just do the data processing. So we know the data facts from the origin data, and we just do the data cleaning. The next is the essential step. We do the data generation using the WGAN GP, which is a very stable GAN framework. And using this GAN framework, we generate the load, CPU, and the memory. So the next step, we reorder the time series. And the final step, we just generate the network data. So the last step is just to do the assessment, just to try to evaluate the synthetic data we generate is really is in good performance. For the first step, data processing, we know the data facts from the origin data set. This is a non-uniform sampling time, and it's they have a non-uniform features from the different source. And it's a non-stationary time series. The load is a main fact, which is a dominant, look like a dominant fact for in the data. So the solution to the data facts, we just resample the data with 1 second, and remove the non-data and average corresponding CPU network data for each node, which is come from the different labs, different source. The GAN models are individually trained for each node, and also is conditioned by the tendency of the load. So the data generation is actually we train WGAN GP, which is the GAN is just we know it's have 2 network basically. One is a generator, another is a discriminator, and the so we use the ResNet to construct the network inside the generator and the discriminator. The random noise will feed to the generator to generate the fake data initially, and also the train set, which is organized by the real data, set to the discriminator, and discriminator try to just judge which data is real or false, is true or false. If the data is false, the next step, next iteration will iterate the new parameters for the generator and the discriminator. On the right panel, it just shows the data we generate from our GAN network. So we use this WGAN GP framework, and actually this is a generative adversarial network, which use a W loss function to just to update the parameters. So here the loss function actually have the two parts. One is just the cross entropy loss term from the distance, and another one is a penalty term. So next I will talk about how to train these GAN models, and here just we demonstrated the result from our GAN network, and the blue one is the real result workloads for the memory free, memory used, and CPU user, CPU system, CPU idle, which is the time for the different workload in the and the red one is just we generate from our system. It's not a big price that the generated workload is very close to a real one. Also, we will show the network, which also trained. The red one is trained from our network, and the blue one is actually from real data, except some noisy or just this fuzzy data, and the tendency is agreeing with our generated network data. To do the estimate, just a synthetic data and the real data, we're using the different from the different angles, from many angles. One is W distance, which is measure the distance between the synthetic data and the real data. So we look at for the different features, we just look at this W distance. Actually, synthetic data is very close for distance is very close to real data. And also we just make for the baseline, we just generate the data from the noise or from random. So which find the distance for the random data is much far from the real one. Another angle is just correlation. So correlation, autocorrelation, we just make measures of autocorrelation for the synthetic data and the real data. So for the each features, you can look, that's the values. Autocorrelation is very close to each other. So which is means the generated data is in a good performance. The distribution is here is also the blue one is a histogram, the real one distribution, and the yellow one is come from the synthetic data. So the distribution is also close to a real one. So now is go to a more interesting scenario. Can we generate workload data by conditions? Which is means the first one is just a high-low workload generation. It means can we just generate the workload is very high, which is a blue case, and also the workload is in the very low level, which is in the red case. So we can generate this data is in a very reasonable way. Next, we need to just to make a combination in the daily workload. So at very early on the morning, the workload is in a very low level, and then go to 8 o'clock on the morning, people go to work, and the workload is just in the media level. After 6 o'clock at the evening, the workload is becomes higher again because people go back home and watch the video, chat on the line, so the workload becomes higher. All this we just can reproduce the workload in a real scenario. And a more complex workload generation is here is one case we show like workload climbs up, and we look at what is corresponding memory and the CPU data. So finally, I just make a conclusion. So here the feature correlation and the work series, time series of information are treated separately. The complicated feature correlation are generated from the well-trained GAN model. But after the generation, the time series information is rebuilt from the conditions. The next one is just the generated workload data is highly reliable and in a good performance. So the more interesting is again generated workload data is adaptive to many scenarios, which are even unseen in the training data set. So that thank you for your attention. Now I'm ready to take your questions.
Thank you very much for your presentation. Do any of the judges have any questions? Okay, I'd like to open up the floor to audience members as well. Does anyone have any questions or comments?
Yeah, maybe I can start from my side. Thank you so much for the presentation. I think this is another interesting problem statement where we can try to enrich the amount of data sets that we have, especially in the situation where in most cases we don't have enough available data set, for example, for training our machine learning models. In your presentation, you have shown that you have used WGAN-GP. Are there other types of GANs that you tried to compare to generate different types of synthetic data and see the performance if the other one is better, or you just tried only one type of GAN?
So this is a pretty good question. So we actually try a lot of the GANs. The classical GANs is not stable. This is well known, and we try this WGAN-GP is because this is the training is very stable. And another issue is for this problem is because we find we try the CGAN or WGAN, the classical WGAN, which is just clipper the parameters. We find that this framework is actually the WGAN-GP framework is very good performance for this task.
Okay, thank you very much.
Does anyone else have any questions or comments?
Hello, I have a short question. Some for the teachers and your novel ideas on the AI technology. So I have a short question on the results. So is there any limitations on your approach? For example, what kind of data can you generate to use your approach? And maybe another kind of type of data is not very effective using your approach. Is there any comments on that?
I'm not very sure your problem, but
I mean, we can use again technology to generate.
Professor Gu,
Yeah.
your microphone, I think maybe you are using a headset, like the microphone is cheaper the sound, so we cannot hear the question properly.
Okay. Let me try. How about now?
Yes, yes, better.
Okay, sorry. I mean, is there any limitations on your, I mean, the data and your approach? For example, maybe some kind of a type of data, you can use your technologies or your approach to generate well, but maybe some types of data are not. So, is there any evaluation on that?
Definitely, I definitely agree with you. So actually the generative AI, which is a very popular AI technique now, is we generate data is really case by case. So which is we try actually in the business, we try a lot of cases. We find that for many cases, we can generate the data and improve the performance of the machine learning, make the performance better. But on the other part, for other parts, we try we try just generate more data and from the generative AI, but we found this data is in a poor performance compared to the real data. So this is really case by case problem, because I think the essential problem here is for the generative data, we don't know which is really be generated and which is not be generated. That's a problem. It's not sure. I think it's even in the academic it's an academic problem. People just look at okay, this data is really be generated. It's the distribution very close to each other, but we're not really sure which is really be generated, which is not.
Okay, thank you.
Thank you very much. Does anyone else have any questions or comments?
Yeah, thank you so much. Interesting work. Maybe quick question. Time series information, you say in the last slide that it is rebuilt from external conditions. My question is, the time series helps in generation, or in your experience, it makes it more difficult for generation?
Because here the problem is they have the two correlation we have to pay attention to, which first one is the correlation between the features. And I think this is really important for this workload problem. Another one we find from this data is a time series correlation or time series relation. And we find actually this relation is highly depends on the load. The load is just the load from the outside. So which data is what determines the CPU performance and the memory performance. So in that case, if we know the external data or the load data, the time series is only determined by this load. So in that case, the time series information can rebuild from load one. But the correlation is different. The correlation between features have to be generated from the GAN. I think that's the reason why we separate the two.
Okay, thank you.
Okay, thank you very much. I think that's the end of the Q&A session. Thank you very much for your presentation.